Let us look at an example of k-nearest neighbor classification. So what you see on screen is a simulation where step 1 says let's create a field. And there's a complexity of 5. So let's just click on create truth. So what this is we have a two-dimensional feature space. So you have x1, x2 being a feature vector. So every point in this two-dimensional space is considered a potential item. And what you are seeing here is you see a bunch of green and white regions. These are the ground truth classification for the items, for the whole feature space, actually. So what you're seeing here is a very complex decision boundary, such that we have a green class region and a white class region. Any point that lives in the green region has a, I guess, green label, but we will see what we use for symbols. So you can keep pressing create truth just to get a sense of, here's a different ground truth that's randomly generated. It has, 3 portions. So these are generated by essentially having linear cuts, but then I randomly assigned a class for each region that is created. So let's do some more just to see, let me find something that's kind of interesting. Okay, so I kind of like this. Let's start with this. So we have this as the ground truth. So this is what the world actually is. If an item is in a particular location, it will have that label. Now, machine learning or k-nearest neighbor does not know that. The way machine learning learns, as we know, is from labeled item. So what we need to do next is to generate a training data set. Okay, so the way we generate a training data set, that's step 2. It will ask you, hey, how many items would you like to generate? Right now it says 10, but let me, for demonstration, let me make it 3. So it's a very small training set. I will use 3 training items. The way I generate these items, they're going to be uniformly sampled across this square. So it's uniform x1 direction, uniform x2 direction, and I'm going to generate 3 points in this way. So let me do that. So let's click on generate samples. Okay, so now you see it. So just by chance, here are the 3 points. So apparently, if a point is lives in the white region and has a white label, I called it a plus. Otherwise, if it lives in green and has a green label, I labeled it as a circle. Now, what you immediately notice is like, hey, 3 points. That's not a lot. It certainly does not cover all the regions, all the ground truth decision regions there is. So, I mean, we should not expect this machine learning to do any good, and you would be right. Nonetheless, let's start from this very small training set, which we have 2 pluses and 1 circle, and just think what k-nearest neighbor would do. So in step 3, this is k-nearest neighbor, and the number 1 there means we are asking for 1 nearest neighbor. Okay, so let's just click on classify and see what happens. All right, so now on the right-hand side, we see the prediction of 1 nearest neighbor. And the way it works is I literally copied the space, but for every pixel, which is every data item, every test item, I enumerate all pixels or all test items in that 2-dimensional feature space. And I ask 1 nearest neighbor to classify each one of them to predict their label. Recall how 1 nearest neighbor works, right? So it is searching for the closest 1 neighbor in the training set of size 3 on the left-hand side, right? So so let's understand why it is doing this kind of prediction. So if you look at the right-hand side plot, we see this interesting green region that looks like a roof, right? So why do we have this roof or triangle shape? The left line on that roof, in between white and green region, you see it is produced by the leftmost plus and the circle. And the boundary there really is just the line that's perpendicular and bisecting the line segment between the left plus and circle. Okay, so that's what we discussed in class. When nearest neighbor, when you compute nearest neighbors, you often get a Voronoi cell boundary that is this bisecting plane. Similarly, the right-hand side of the roof that is produced by the right plus and the circle. So if you extend that, you will clearly see it is also the bisecting line, okay, between those two trending points. Now, the reason why this right-hand side roof line doesn't go all the way to the left is because we have the two pluses, and that's kind of making everything in between those the two pluses, they're also white. Okay, so if you look at step 3, on the right-hand side, there's an error rate which equals 55%. This is the error rate considering every pixel in this two-dimensional square. And we classified it with one nearest neighbor, right? But then we compared it against the ground truth label on the left-hand side. So this is essentially a test set error rate. And the test set error rate of 55 is terrible. It's very large. And of course, we see that because we don't like the way things classify. All right, so let's do this. Let's increase the number of training points from 3 to, let's say, 30. So I'm going to make it 30 times more 10 times more training items. So I'm going to click on generate samples. This is going to be random sample. So I just get a new batch of training points, and here we have 30 training points. They're random in this 2D space on the left-hand side, and they are labeled by the corresponding ground truth region. So, okay, so let's look at that. Now, let's still do one nearest neighbor in step 3. I'm just going to click on classify now. What you want to monitor is what happens to the right-hand side prediction, as well as what happens to the error rate. So here we go. Now, this predicted decision boundary, it's way better than what we had with 3, but it's still not faithful to the ground truth. If you look at the error rate, it is better. It is now 22%, but still not great. And that is very intuitive. You can compare the two plots and see, hey, the boundaries really do not match that well. Nonetheless, the points are sort of somewhat representative of what the ground truth regions on the left-hand side is. So, on the right-hand side, if you really squint your eyes, you will say, yeah, more or less, but not very close. So another thing is you should be able to, at least roughly speaking, interpret why the right-hand side one nearest neighbor prediction is producing those decision boundaries. Try to do that. All right, so so now we see that, yeah, okay, it seems like more training points is useful. Let's do it again. Let's generate 10 times more training points. So I'm going to do 300 training points. Again, I'm going to click on generate sample. So it's going to be a fresh random training set. All right, so here we go. This is random, uniform 300 points, okay? Still one nearest neighbor. Let's monitor the error rate as well as the shape. So here we go. All right, so the error rate now, as you can see, goes down to about 6%, which is way better. And the right-hand side plot, yeah, I know it's interesting, right? It's like an artistic rendition of what's on the left-hand side. The decision boundary is certainly not the straight lines that we have on the left-hand side, but that is because of the nature of one nearest neighbor. It's really all those Voronoi cell boundaries. Okay, good. So now we see clearly that yes, more training data points is useful in producing a better prediction. Okay, and that's intuitive. Now, let me try this. I think it will not crash my program, but let's generate 3,000 points. And do I want to do that? Maybe not. Let me do 1,000 data points and generate samples. All right, so this is a very dense training set now for the little feature space that we have. Let's see how this performs. So let's look at error rate again. This goes down to about 4%. And on the right-hand side, you see the decision boundary. You know, it's getting more and more close to the left-hand side, but the boundaries are still sort of wiggly and so on and so forth. And another thing you notice is sort of we have a diminishing return. Even if we used a lot more training examples, the error rate decrease is not that great. Okay, so that's all interesting observations. Now, I'd like to do this. Let me go back to a reasonable number of training points. By the way, like, you know, if you have such a small training set, we have a field size of 80 pixels by 80 pixels. That's like 6,000 unique points we could have. We're already calling for 1,000 training example. That's like 1/5 of the world, and that's a lot. In practice, you certainly wouldn't have a lot of that. So let me go back to perhaps a somewhat reasonable situation. So I would say 30 training points. It's not a lot, but it's somewhat reasonable. Okay, so here we have a new set of 30, right? Let's do 1 nearest neighbor classification again. Okay, so we go back to this 20% error rate. Okay, so that's what it is. But now let's try to see how k, like in terms of number of neighbors, how that k affects classification. So I'm going to change k now. So instead of 1, let me do 3. The reason I do 3 is because we have binary classification, 2 classes. And if you do 3 neighbors, k equals 3, you always have a unique majority in the neighborhood. So you don't need to randomly break ties. So let me do 3. Recall, for 1 nearest neighbor, the error rate was about 19.3%. So let's do 3 nearest neighbor. It gets worse, right? The error rate is worse. It's 23 now. And another thing you might notice is like, hey, there's less predicted regions. And in fact, the predicted regions seems to be a bit more smooth. Let's see if that trend is holding. So let's move on to 5 nearest neighbors and do classify. Aha. So the error rate is even worse, like 33%. The decision boundary now seems to be almost like a straight line with somewhat wiggles. Okay, so it's definitely getting worse. Now let's try even higher k, so 7. So I think the error rate is sort of stabilizing a little bit. So let's keep going. 9 maybe. Okay, so yeah, we're seeing all these things. So let me make some bigger jumps. So how about 21? Okay, so the error rate sort of is stabilizing. What I want to show you is, how about 29? Aha! So at this moment, you should think what happened. Why is it predicting everything as green? And the error rate is kind of high. All right. Now, you might be curious, what happens if I, instead of doing an odd number of k, if I do, let's just say we ask for 2 nearest neighbors, what will happen? Right, so when you ask for 2 nearest neighbors, there will be points that are potentially on the equidistance to both neighbors. So in that case, my app here actually just will predict a label randomly. So let's see what happens with 2 nearest neighbor. Okay, so that's what happens. Those interesting patterned regions, That's because points in those regions have two neighbors that are of different labels. Not necessarily equidistant, but just two neighbors with different labels. And so for each test point, I'm flipping a coin to break the tie randomly. So that's why you see this patterned prediction. All right, so that's a demo of k-nearest neighbor.